C.2. Now we define asymptotic notations. After C.1, so you get an idea how to compare orders of growth of two growth functions. Now, this topic, C.2, we want to provide rigorous definitions for these asymptotic notations. Yeah. All right. The first one, big O notation. Yeah. Big O. Yeah. So when we write, not little o, you saw little o before, but this time we want to define big O asymptotic notation. Okay. Yeah. So let's look at the official definition of this big O notation. Yeah. All right. For a given function g of n, the notation big O of g of n represents the set of functions f of n that satisfy the following condition. There exists some positive constant c, only one, remember, one bound, upper, lower, this one we only have one bound, not both. So there exists some positive constant c and some non-negative integer n0. Here, another. I didn't mention this, the second special number before, but here we need it. Some non-negative integer n0, such that this inequality, we only have the upper bound, f of n less than or equal to c times g of n, when the range for all n greater or equal to n0. Here we add this condition. Because the reason, so we want to make here, we want to make a rigorous definition. So when we consider this inequality, it may not hold all the time. It may not hold all the time. Okay? But after we skip a few numbers, after we pass this line, this is one line, okay? N0, so there is a line here. After our variable n passes this line, n0 line, then this inequality always holds. That's the exact meaning. Okay? Before this line, n0 line, this inequality may not hold, but don't worry. Even if the inequality does not hold before this line, we do not worry. The reason is simple. Remember, when we compare order of growth, we only worry about the case when n is very large, right? We don't worry about the case when n is relatively small. Okay? So if n is before this n0 line, we treat this n is relatively small. So we do not need to worry because our computer is very powerful. Our computer can handle relatively small problem sizes easily, right? So we have the confidence on the power of our computers. But our computing power has some limit, right? So has certain limit. So when the size of n is very large, then we need to worry about our computing power may not be good enough. Okay, yeah. So that's the role of the special n0 number placed here. Okay, yeah. We need it. We need some special n0 number. Yeah. So for this special n0 number, yeah, so sometimes we use another way to describe it. Yeah, the special n0. We say, yeah, so this number, you have freedom to choose, right? Yeah. Before you make your selection, you have freedom to choose. 100, 1,000, 1 million, even 1 billion, you have freedom to choose this n0 number. But after you select it, it must be fixed. Okay? Yeah. After you select the n0 number, then when you change the value of n, you should not change the value of n0 anymore. Okay? You have to fix it. Okay? Yeah. So that's the way you choose the special n0. Okay, yeah. So then we have a special way to call this n0 condition. Yeah, because sometimes we may not like to mention this n0 number explicitly. Yeah, we know there is some number, yeah, but we do not need to, give the specific number for this n0. So we usually say when n is sufficiently large. Yeah, you can see in this condition, when n is sufficiently large, you cannot see n0, right? You cannot see n0. Okay, yeah, yeah. So for the last, this last condition, yeah, if I use this n sufficiently large, I can say in this way. So I can bypass n0 representation. I can say in this way, there exists some positive constant c, yeah, such that f of n less than or equal to c times g of n when n is sufficiently large. So we do not need to talk about n0 explicitly. Yeah. So that's another way to get around explicit n0. Yeah. But they have the same meaning. Yeah. They have the same meaning. Yeah. But in some questions, sometimes we need to find those n0. Yeah. We need to find after our problem size variable n passes what special number n0 the inequality holds, the upper bound or the lower bound, or both upper bound and the lower bound are there. Okay, yeah, yeah. So this is the big O notation, formal definition. Yeah. Similarly, we can have other definitions. Yeah. All right. Yeah, but here, before we move to another definition, yeah, so we use a graph to visualize this relationship. Yeah. All right. So we have a G function first. Yeah. But in order to describe this f function, we need to adjust constant multiple of g, c times g of n. We can choose that constant c. So we can, move the curve up or down when we change the value of c. Yeah. Yeah. Until the graph of this curve is above the curve of f of n, but remember this vertical line, n0, this vertical line, yeah. At the left-hand side of this vertical line, yeah, we don't worry about so which curve is higher, which curve is lower. It doesn't matter. Okay, yeah. But after this line, at the right-hand side of this line, then we need to make sure C constant multiple of G of n, its curve should be completely above the curve of f of n. That's the meaning of this definition. Yeah. So the visual understanding, like this one, this graph. Yeah. All right. So let's look at another asymptotic notation. This time, big omega notation. Yeah. All right. So the previous one, we have the upper bound. How about the lower bound? So this one, we want to see the lower bound case. Yeah. The definition almost the same, but we change to the lower bound. Yeah. And the asymptotic notation, this time we use this big omega notation. Okay. Yeah. Also constant C, non-negative integer n0, such that this time f of n greater or equal to C multiple of G of n. When for all n greater or equal to n0. Passing that n0 line, the same as before, yeah, but just for the lower bound version. Yeah. We can also look at the relationship using this graph, but this time we adjust constant C such that C multiple of G of n is completely below the curve of f of n when we need this vertical line, when n passes this n0 vertical line. Yeah. Before this vertical line, even if it's not true, even if the curve is like that, okay, it doesn't matter. Yeah. So we don't worry. Yeah. Yeah. But we want to make sure after certain vertical line, that relationship, that lower bound relationship must hold. That's the big omega notation. Yeah. Big omega. Yeah. Only one side bound. Yeah. Next, we want to see two side bounds, big theta notation. Yeah. So the description similar, this time we use big theta. Yeah. Remember, when we use the limit, we also have that big theta case, right? Yeah. But here in our inequality way, we have the definition for this big theta case. Yeah. But this time we have positive constant C1 and C2, and also non-negative integer n0, such that inequality, two bounds, lower bound C2 multiple of G of n, and upper bound C1 multiple of G of n. Still, n should be greater or equal to n0. Yeah. From the graph, this time we have both upper bound, lower bound, like this. Okay, yeah. So then we use the big theta notation. Yeah. So here you can see how many notations do we use. Yeah. So far at this point, we have 5 different asymptotic notations, right? Yeah. Big O, little o, big omega, little omega, big theta, big theta. Yeah. 5 different asymptotic notations. Okay, yeah, yeah. All right, yeah. So after these definitions, yeah, so that's all we need for this class. Now, try to get yourselves familiar with these abstract asymptotic notations. Okay, yeah. So that's all we need for this class. Yeah. Yeah. Actually, some of the notations we may use more. Yeah. So I like to say, yeah, these 2 asymptotic notations will be used the most. Okay, one is big O of G of n. Another is big theta of G of n. These 2 asymptotic notations will be used the most. Okay, yeah. The other 3, yeah, so we do not use them much. Okay, later in our discussions, we mainly use these 2 asymptotic notations. Okay, yeah, so not too hard. Yeah. Big O, we have upper bound. Yeah. Big theta, we have both bounds, lower, upper, both bounds. Yeah. All right.